So I wanted to go over the derivation of the wave equation in a video because I didn't want to take the time in class, but it's certainly something that you should be watching and thinking about what the significance of it is, because the wave equation in physics is actually really important. It's a partial differential equation that the solutions of that equation describe a wave, a linear wave. And those are the types of waves that we're studying in this chapter. So you should have gotten to the point where you have seen that the way that we're going to describe our waves is using the sine function. These are traveling waves. They have a sinusoidal shape to them. And we're looking at transverse waves. Those are the ones that would really sort of look like we might visualize a wave if we were just asked to. We would instinctively think of like ripples in a pond, and that would be a transverse wave. Remember that the transverse wave, the disturbance or the movement of the medium is perpendicular to the motion of the wave itself. Also, let's just remind ourselves that when we describe the wave, it depends on two different variables. It depends on position, so what the wave will look like will depend on what location you're focused on, but it also depends on time because it's a moving disturbance. And so if you, for instance, position yourself at a particular location, then you will also see that in time, the way that that wave looks is going to change. A lot of times when we picture a wave, we have to have taken a snapshot of that wave, of what it looks like at a particular instant in time as well. So getting your head around these two variables and how they both play into what the wave looks like might take a little while, but it's important that you understand that this expression right here depends on both of those variables: the position, where are you, and when are you looking at it. Now, if we looked at the velocity of a piece of the medium, we would really be wanting to look at how the derivative of this wave with respect to time. We write it in that funny notation because this is a partial derivative purely because of the fact that y depends on two different variables. So writing the partial with respect to time means that we're only really looking at how this expression of y is dependent on the time. So we're only taking the derivative with respect to time. That means, what do I do with the x? I just treat the x term, the piece of it that depends on x, as a constant. So you might be feeling a little overwhelmed because you haven't covered partial derivatives in your math class. But the fact of the matter is, it doesn't really matter. You know how to do partial derivatives if I tell you. You just treat the other variables as constants. So it's just like they're numbers. So if we take the derivative of this expression for our wave, the first thing we would do, we have to use the chain rule. We would take the derivative of the sine with respect to time. And so that's going to give me a cosine of this whole expression. And then we take the derivative of the argument of that angle, which is this piece right here, with respect to time. Again, keeping in mind we treat the kx and the phi as constants, so nothing happens there. So I get a minus omega. And so this ends up to be minus omega a cosine of kx minus omega t plus phi. Again, keep in mind that this is the velocity of the motion of the medium as the wave is traveling through the medium. The medium is oscillating up and down. It actually is oscillating up and down like a simple harmonic oscillator, if you want to think about that. That's really important. And so we're looking at what is the velocity of that medium as the wave travels through it. And it's in the direction that's perpendicular to the motion of the wave, which would be in the x direction. Now, if we also then look at the acceleration, we're just going to take the derivative of this again, And so I could write that either of this way. I could make it the second derivative of y with respect to time, or I could just think of it as the first derivative of the velocity. So if minus omega a, and then I take the derivative of the cosine, which is minus the sine of kx minus omega t plus phi. And then I have to take the derivative of the angle of the sine, which gives me a minus omega. So I got a lot of negative signs here. I want to keep track of all of them. I actually get minus omega squared a times the sine of kx minus omega t plus phi. Okay, so we've looked at those two terms again. What this term represents is when we're looking at the medium, and as the wave passes through it, the medium is moving up and down. Remember that picture from your book of the seagull? As the wave travels past the seagull doesn't move with the wave, he just kind of bobs up and down. So we're looking at those motions of the up and down as the wave goes past that location and talking about what the velocity and the acceleration look like. So now we're going to take the derivatives. Now we're going to look at also with respect to x, because these first two derivatives, we were concentrating on how that wave function depends on time, but we also want to think about how does it depend on position. Now, when we're doing this, you could be thinking, now, backing up a little bit, when we were looking at these expressions, in a sense, we were sort of focused in on a particular location, so we were fixing x, we were sort of thinking about what does a particular position look like as the wave travels through it. Now, when we take the derivative with respect to x, we're going to keep time constant. So this is keeping x constant. Now we're going to keep the time constant. That might be a little bit easier for us to think about, because what we're really doing is taking a snapshot of the wave, taking a picture, what does it look like, and how does it change with as we look at x. So the derivative of that wave function with respect to x is actually the slope of the wave at a location x. I mean, that's what we're really doing it at some time t. And if I take that derivative, again, I'm starting here, I get the derivative of the sine, which is cosine. And then I have to take the derivative of the angle, which is, I'm just doing kx, and so that gives me a k. And so this gives me ka cosine of kx minus omega t plus phi. The second derivative and what does the second derivative represent? Represents the concavity of the wave function, because again, it's like looking at a graph of y versus x. And if I do that, I'm going to get ka times minus sine of kx minus omega t plus phi, and then multiply it by a k. And so this is equal to minus k squared a sine of kx minus omega t plus phi. Now, what we're going to do here now is we're going to take the ratio of these two terms. We're really kind of most interested in the concavity and the acceleration term. And we're going to take a ratio of the acceleration to the concavity. And that's going to actually result in the wave equation. So the acceleration, first of all, I could say I write it as the second derivative of y with respect to time. The concavity is the second derivative of y with respect to x. The acceleration term ended up looking like minus omega squared a sine of kx minus omega t plus phi. The concavity term ended up as minus k squared a sine of kx minus omega t plus phi. So those cancel out, the negative signs cancel out, and I'm left with d squared. If I want to sort of rearrange it, and just reminding you of some things that we learned about as we went through this chapter and learned about waves. The omega is the angular frequency. Now that should be a review from when we did harmonic motion and is equal to 2 pi times the frequency. K is a new constant for us. We call it the wave number, and it's equal to 2 pi over lambda. And what I want to call your attention to is this ratio right here, because if we put those terms over each other and we use the fact that we know that the velocity is equal to the frequency times the wavelength, we'll notice that if we put omega squared over k squared, that actually is equal to v squared. Now, it turns out that most of the time when we see the wave equation, it's expressed like this. We're just dividing through by the v squared. And this is what we were actually after. So when we worked with all these expressions and did this manipulation, we actually came up with what we call the wave equation. Like I said at the beginning, this is a really important equation in physics. Now, the way that it works is y, the function y, is the solution to that equation. It's a partial differential equation, but we're just going to be happy about that and not get too freaked out about those words. And basically what we're saying is that any function y that is a solution to this equation would describe what we would call a linear wave, which is a wave that is going to result from some sort of linear restoring function or restoring force of the medium. That should you should kind of think about restoring force as we talked about the simple harmonic oscillator. We talked about the restoring force of a spring. So the idea is that there's a force that tries to kind of restore the medium back to its equilibrium position, and think about the fact that as the wave travels through the medium, the piece of medium actually does oscillate like a simple harmonic oscillator. So all this should be sort of making connections. But in any case, the solution to this equation will describe a wave, and that wave will be traveling with the speed of v, and that is the wave equation. So now you know how we get at that.